Hey guys, I realize this is not the most sophisticated way of doing this, but I just wanted to do a little walkthrough of NMR assignment for one of the Chalcones here, just in case it's helpful for any of you out there that are still looking to do the assignments for either the Chalcone itself or the hydrogenation products that you guys made. Okay, so in this particular case, the chalcone that we're looking at has the chlorine and the fluorine substituents on it. The first thing that you want to do is to take a look at the type of protons that you have. This is, of course, after you've done your integrations and peak assignments. And so the types of protons that this particular compound has are aryl protons and the alkene protons. And we expect all of those to be in the downfield region. And in this case, we do see that. And so it's all between 7 and 8 ppm. We do see a peak that's up here that's at 1.62, and the reason for that is because that actually belongs to trace water that's in your sample. So that ends up being water that's there. This inset that you see here is actually just a blown up region of what you see here, just so you can see the splitting. The other peak the one peak that you will always be able to assign right away is the NMR solvent that the sample was run in, and that is deuterated chloroform in this case, and that shows up at 7.26, and so that's right here. All right, and so then the next thing that you want to do is, well, what I like to do is I'd like to write down all of the different unique protons, how many belong to each letter, and then the splitting for each one of them. So it looked like most of you had already done the assignments for your lettering for your protons in lab, so I'm not going to go through that, but we have A, B, C, D, E, and F here. And so I'm just going to walk through and just put down the number of protons that belong to each one of those. So for A, it's going to be 2, B 2, C is 1, D is 1, E is 2, and then F is 2. So I'm just going to write that down here. Awesome. Okay, and then the next thing that I do is I like to write down what the splitting pattern is for each one of them. So A is, remember, it's going to be n+1, so it's +1 next to however many are adjacent. So there's 1 adjacent next to A, so that's going to be a doublet. n+1 makes that a doublet. Same thing with B, it's only on this side that there's a proton, so that's a doublet. C, there's only 1 proton here, and it's only next to one other one. There's nothing on this other side, so that's a doublet. Same thing with D, and then E is the same situation where you have that, and then F only has 1, so that is also a doublet. All right, so we have all doublets as our splitting pattern, which is actually kind of inconvenient because you can't use splitting as a way of differentiating the peaks that you have as far as making assignments is concerned. So what that means is you're really going to rely on understanding chemical shifts, so like what affects moving the peaks further downfield or upfield. And the other thing, the biggest one, is going to be your use of your integrations. So hopefully you guys went ahead and did that, and if you have questions about that, you can let me know. So here what we're going to start out with is by looking at the inset that's here. And one thing that I want to point out is that you probably see a triplet here. This is undeniably a triplet, but we're like, hey, we only assign doublets, so what's going on? And the explanation for that is because of the existence of this fluorine that's here. So the reason is that, so F can be split by proton E. Well, it turns out that fluorine has a spin state that is able to couple with protons as well, and so you actually get splitting when you're adjacent to F. Essentially, you could adjacent to fluorines. So if you could actually just treat fluorines a lot of times just as if they were another proton. And so F actually ends up feeling like it's next to 2 different protons, so n+1 for that actually ends up being 3, and so this is actually going to be a triplet. And so this triplet that's here actually belongs to proton F. The next one that's probably the easiest to assign would be these guys that are only worth 1, right? Because there's less of them. And so two things that you could do. One is you could take a look at your integrations here and see what goes to 1, and we luckily have this guy that integrates to 1, and we have this one that integrates to 1, and that ends up being this guy here and this guy here. And something that I want to point out is that these 2 peaks look alike, and what I mean by that is that the space between the peaks are similar, and the spaces between here are larger than, say, this peak that's here. And this is actually so far apart that some of you might have even integrated these as singlets, but they are, you would also see, if you did that, you would see that these probably integrated to 1/2. And since you can't have half a proton, they belong together and they're actually a doublet. So when they look similar, what that means is that chemically their environment is similar as well. And so that would make sense that, these are both alkene protons that are next to each other. And so they look the same, or they look similar, I should say. Okay, so now we know that these belong to the alkene, but which belongs to which? So the information that you can use is that resonance structure that we drew in pre-lab. And so remember, you can push these electrons to make that enolate resonance structure where you have this positive charge that sits on this carbon. And what that does is that de-shields that proton that's sitting on there, and then that makes the peak go further downfield because it's feeling that magnet more. So what that means is that this guy here is going to be assigned as C, and that this guy here is going to be assigned as D. All right, so now we have C, D, and F done. And so what we have left are A, B, and E. So the next one that you might want to try and assign is whatever is furthest downfield. So things that cause peaks to go downfield, basically anything that make it de-shielded. So substituents that are electronegative will do that. As we saw here, resonance structures that allow positive charges to be created, that will also do it. And so one other resonance structure that I didn't mention in class is the possibility for these electrons here going into here to also make that enolate. And so what that would do is that would put that positive charge sit on this carbon here. That would make proton E very de-shielded. And so actually what that ends up being is that this is actually going to be proton E that sits very, very far downfield there. So now we have just A and B that are left to assign. And like I said, these are going to be very similar in environments. And so we have A and B that are here. And so we actually should be looking at this structure here. If this is a positive charge that's sitting here, you can imagine that there's going to be more electron density that's being pulled away. And so B is going to feel it more. And so this is actually going to be B, since it's more de-shielded, and this guy will be A. This is a little tricky because A is sitting next to the chlorine, so some of you may have assigned this one as A and this one as B. Honestly, if you give me your justification for your assignments, that's all I'm really looking for. I know that this can be a little bit tricky and a little bit nuanced, but hopefully this gives you a better idea of how to go about making these assignments, and knowing things like that fluorine can cause coupling in addition to other protons. As always, if you guys have questions, please don't hesitate to email me. I do have office hours still this week, and hopefully this is helpful.